Hello guys and welcome. So right now we are going to discuss about the volcanoes and other igneous activities. So these are the nature of your volcanic eruptions. So the factors uh, affecting your volcanic eruptions um, is based on the composition of the magma, the temperature of the magma, and also the dissolved gases in the magma, and also its viscosity, but that is rather related to your temperature and your composition of your magma. Now, for your composition of your magma, as we previously discussed on our class, the more felsic or the more silica content that the magma has, kinda the silica makes uh, creates like silica chains that binds the magma together. So the more silica the magma contains, the more chains that it um, yeah, that it makes, and therefore it results into a very high viscosity magma. Okay, so the more silica, more viscous it is, and the more it is resistive for an easier flow. And if it resists an easier flow, it may result into a uh, buildup of build. It can build pressure for in the magma chamber, and therefore it will erupt. Okay, and then we have here the temperature of the magma. Of course, when the magma cools, uh, it slowly becomes rock, and your rock is somewhat more will not flow freely, and if it will not flow freely, same as viscosity, uh, and it is also a factor of viscosity. um, the cooler your magma, the more it is resistant to flow, and if it is resistant to flow, then it is explosive. And your dissolved gases in your magma. So dissolved gases, sulfur, carbon dioxide, water vapor. Um, these can also affect your magma. And the more dissolved gases is contained in your magma, the more viscous it is. Okay, so viscosity. So as discussed earlier, temperature, the hotter gases are less viscous. Composition with the high silica, high viscosity, low silica, more fluid or more fluid. And dissolved gases mainly are water vapor and carbon dioxide. So gases expand at the surface, and a vent is an opening in the in the surface of the earth. Through molten rock and gases are released and provide the force to extrude lava. So the violence of an eruption is related to how easily the gases escape. So if it has more, if there are more vents for your gases to escape, the less explosive will be your eruption. And these are your magma compositions. So basaltic, so uh, silica is at least e approximately 50%, gases at 1 to 2%, and your tendency for from pyroclastics are the least because these are the most fluid flowing magma. And you have here at the other side of the spectrum, you have rhyolitic, which is more or less 70% silica with the viscosity at the greatest and the gas content at 4 to 6%, and it has the greatest. And these type of magma are the most explosive type of magma. Now you have your volcanic materials, your lava flow. Basaltic lavas are more fluid, and types of lava we have the pahoy-hoy, which resembles braids and ropes, and usually these are the indicators that your lava was flowing fluidly. And you have your which is rough and jagged blocks, which is an indicator that your lava does not really flow or it flows viscous. And you have your gases, 1 to 5% of magma by weight is mainly water, vapor, and carbon dioxide, but it's more of the side of the water vapor. So this is a good example of your pahoy-hoy or the ropey lava. As you can see over here, these are actually ropes, or in some uh, other people would describe it as braids. Okay. This is a slow-moving aa. So as you can see, there are two people uh, in the photo that are actually just walking. Now we have your pyroclastic materials. Your pyroclastic materials is the given name for your particles produced in volcanic eruptions. The fragments ejected during the eruptions are ranged in the size, very fine duct and volcanic ash, and they are similarly classified in your like your sedimentary classic sedimentary particles and to pieces that weigh several tons. Although they are classified similarly, we use different terms for pyroclastic materials. So your types of pyroclastic materials, you have the ash and dust. So these are fine and glassy fragments. The pumice, which is frothy and air-filled lava, and the lapilli, or the walnut-sized particles, and cinders for pea-sized particles. For boulder-sized or larger than lapilli, rather, so blocks, they are hardened lava. So they to differentiate your blocks and bombs, your um, your blocks are rather rough in shape, and because they exited the volcano as hard rock. And for your bombs, they are ejected as hot lava, and so they are rather soft. Uh, they are what do you call this? Soft projectiles flying out of the volcano. So as they fly out, they form more aerodynamic. So uh, they are more rather streamlined position. So they more or less have uh, in a like a American football shape. Then the types of volcano. So there are three main volcanic types. They are shield, the cinder cones, and the composite cones. And the anatomy of the volcano. So a volcano basically is a mountain formed of lava and or pyroclastic materials. And you have a crater, which is the depression at the summit of a volcano, of where the lava or where the lava flows out. And the conduit or pipe or a vent carries the gas-rich magma to the surface. So here it is. So you have the crater, the vent, and some other smaller vents. The volcanic neck. So this is an example of a um, composite volcano with alternating lava and pyroclastic materials. So types of volcanoes. Now we have the shield volcanoes. They are broad, gently sloping volcanoes from uh, fluid basaltic lava. They are broad because your lava is flowing more freely, more fluid, so they can travel farther. Okay. Now you have your cinder type volcanoes, which are very small volcanoes built primarily from of pyroclastic materials ejected from a single vent. So they have a rather steep slope and small size. Frequently, it occurs in groups. So this is an example. This is Mount Kilauea, if I'm not mistaken. So this is rather a very large volcano. Okay, so this is in Hawaii, and this is your cinder type volcano. So it is a small volcano with a crater in the middle. Usually, it releases your pyroclastic materials. And then lastly, we have the composite volcanoes, which are composed of both lava flows and pyroclastic materials. So most are adjacent to the Pacific Ocean because around the Pacific Ring of Fire or the Pacific Ocean, there are actually convergent boundaries which produce these types of volcanoes. So they are large in size, but smaller than your rather smaller than uh, your shield volcanoes. They are interbedded lavas and pyroclastics and mostly violent type of activity. And this is the example of Mount Rainier. So another composite volcano. This is Mount St. Helens before and after the eruption in May 18, 1980. So as you can see here, this is Spirit Lake. And after the eruption, this was filled with your uh, volcanic materials, and the whole landscape has been erased. So this is a size comparison. So Mauna Loa, your Mount Rainier, and Sunset Crater, a large cinder type, considered large cinder type. So this is rather small. Other volcanic landforms, we have the calderas, which are large depressions in volcanoes. They're nearly circular and formed by a collapse, and the size exceeds 1 kilometer in diameter. If it is smaller than your 1 kilometer diameter, it is called a maar, MAAR. We have the lava plateau, which are fluid lava extruded from crustal fractures called fissures. And usually, lava plateaus are a result of a very large volcanic event. And now we have plutons. We discussed earlier about the caldera and the uh, lava plateau, which are uh, extrusive igneous formations. Now we are in the plutons. So plutons are intrusive igneous structures that result from your cooling and hardening of magma beneath the surface of the Earth. And the intrusive igneous bodies or plutons are generally classified according to their shape, size, and relationship to the surrounding rock layers. And we have the seals and laccolith. So these are plutons that were formed when the magma is intruded close to the surface. So your seal resembles a buried lava flows and exhibit columnar joints. So they may be mistaken as something as a sedimentary structure. And their laccoliths are lens-shaped masses that are arced or overlying strata that are lens-shaped upwards or uh, parabola upwards. So this is an example of a sill. So they are horizontal with sedimentary rock layers that was that were what do you call this, overlying and underlying the intrusion. So so to classify this between to differentiate this as a seal and a lava flow, you should look at the texture of the rock that is in contact with your sedimentary layers. So if it was a an intrusion, there should be some minor metamorphism in the boundary of the sedimentary layers and also in your basalt. Okay, so if there is no present minor metamorphic uh, minor metamorphism or diagenesis in your sedimentary layers, then this is a flow rather than a sill. And dikes, these are similar to sill, but rather instead of taking horizontal orientation, your dikes cut through your sedimentary layers. And many dikes form when your magma from a large magma chamber invades the fractures of your surrounding rocks. And you have your batholiths, which are large masses of igneous rocks that formed when your magma intruded at depth, has been crystallized, cooled, and subsequently was exposed by an erosion. And, and for it to be considered as a batholith, it should be 100 square kilometers to be considered one. If it is less than 100 square kilometers, then it should be classified as a stock. So this is an example of a batholith. This is a large igneous, intrusive igneous rock that was exposed to the surface, and this was once underground. So this is how a batholith is formed. Now you have your magma chamber. When it crystallizes, it becomes solid rock, and further erosion of the surface is where you have a batholith. And the origin of magma. So your geologists, we conclude that the magma originates when essentially a solid rock located in the crust and the upper mantle partially melts. And that is obvious in the way that generate magma from your solid rock is to raise the temperature above the level at which the rock begins to melt. And the role of heat. So we have the geothermal gradient, which is approximately 1 kilometer for every 25 to 30 kilometers below. So, but that only works in the crust. So the Earth's natural temperature increases with depth, but is not sufficient enough to melt the rock at the lower crust and the upper mantle. So additional heat is generated by the friction in the subduction zones. So the friction in contact between your subducting slab and your overriding slab, and the crustal rocks heated during the subduction zones and the rising hot mantle rocks. And the role of water. So your water is actually can help in uh, your melting of your rock. It acts as a catalyst, so causes the rock to melt at a lower temperature and plays an important role in subducting oceanic plates. So this is an example of your what they call this, of a fissure eruption of in a basaltic magma. So basaltic magma, as discussed earlier, are free flowing magma. So as discussed in the previous lecture, the basic connection between your plate tectonics and volcanism is that um, they provide your mechanisms by which your mantle rocks melt and generate magma. So you have the oceanic convergence, where rising magma can form volcanic island arcs, and your oceanic continental convergence, wherein the rising magma can form continental volcanic arcs. So a good example would be Aleutian Islands. So this is Mount Pinatubo, a convergent boundary volcano. Now we have the divergent plate boundaries, which play the greatest volume of volcanic rock is produced along the oceanic ridge system. We have the lithosphere pulls apart, less pressure on the underlying rocks, where the partial melting occurs, and therefore your large quantities of fluid basaltic magma are produced. And now we have the intraplate volcanism. This is an igneous activity that occurs within a tectonic plate away from the plate boundaries. So most intraplate volcanism occurs where a mass is hotter than normal in the mantle. Material called a mantle plume rises towards the surface, which becomes a hotspot. So, a good example are the Hawaiian Islands and the Columbia Plateau. So, this is from Mount Kilauea, and that ends our lesson.